Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I am dealing with spectroscopy for chemistry. This is the lecture of IR spectra and lecture number 14. In this I will explain you again factors affecting IR bands. So we were discussing in previous lecture about intermolecular hydrogen bonding and intramolecular hydrogen bonding, and at the end I could not able to complete this difference between these two. That's why I am repeating this part once again. So intermolecular hydrogen bonding in IR spectra. So we can see that if there is intermolecular hydrogen bonding, you will get a broad IR band, and if there is an intramolecular hydrogen bonding, we will get sharp and well-defined IR band. So in case of intermolecular, we have broad band, and here intramolecular gives sharp band. Next is it has effect of dilution. That means in concentrated solution, you will find the effect of intermolecular hydrogen bonding, but as amount of solvent increase, that is due to dilution, then number of intermolecular hydrogen bonds will decrease, and that is why you will not see the effect of intermolecular hydrogen bond in IR. So this way you will find that due to intermolecular hydrogen bonding there was a broad band, but now due to dilution it becomes sharp band. Well, intramolecular hydrogen bond is a matter of internal problem. It's of own molecule, and therefore even if you dilute the solution, there will be no change in the band, IR band of that particular compound which carry intramolecular hydrogen bond. So there is no effect of dilution. So that is the case in intramolecular. Now we will see third difference, that is frequency difference between free and associated molecule. That means the one which is having hydrogen bond is remarkable. So you find quite a change between the frequency value of free molecule and the one which is having hydrogen bonding. Here, in case of intramolecular hydrogen bonding, the frequency difference between free and associated molecule, those who are having hydrogen bond, is very small. So it is not so remarkable. So this is all about the difference between intermolecular and intramolecular hydrogen bonding. Okay. So now we'll go ahead with the next effect, and that is field effect. In case of ortho-disubstituted or ortho-substituted compounds, the lone pair of electrons on two atoms influence each other. For example, here we have C double bond O group And at ortho position, if there is halogen, then these two electrons repel each other and therefore they will change the geometry of this molecule. Okay, so the non-bonding electrons present on oxygen and halogen cause electrostatic repulsions. And this result in a change in the state of hybridization of C double bond O group, carbonyl group, conjugation is diminished and absorption occurs at higher wave number. Thus, with respect to trans isomer, cis isomer absorbs at higher frequency than the trans isomer. For example, we can take orthonitrophenol. This is orthonitrophenol, in which you will find interaction between hydrogen and oxygen as well as nitrogen and hydrogen. And this can be compared with paranitrophenol. So here OH band in case of orthonitrophenol appear at 3445 and 3240, while in this case paranitrophenol the band is at 3365 centimeter inverse. N double bond O stretching here appear at 1530, which is asymmetric stretching, and 1310 centimeter inverse, which is due to symmetrical stretching. While in case of paranitrophenol, the value is 1495 for asymmetric stretching, and 1340 for symmetric stretching. So here, this is due to more symmetry. This will reduce delta mu, and therefore it will reduce frequency also. Okay. So this is the case. Now, if one sharp peak appear at around 690 plus or minus 10 centimeter inverse, it is due to ring bending, which is present in meta-isomer. So this way we can identify ortho, para and meta-isomers with the reference of IR bands. Okay. So that's it in this lecture. Thank you so much.